All right, so chapter 7 is going to be a discussion of graphing in images. Okay, we're going to be doing antiderivatives in chapter 7. That's going to be the focus of what we're doing. And we're going to be doing it for things specifically after 7.1 in 3 dimensions. That's the visualization part, okay? What you're going to see happen in 7.2 and 7.3 is I'm actually going to show you some videos that they're just online that I found. And they're really good because the gentleman who is doing them is very good at drawing the pictures for us to help visualize them. And I'm not as good as he is. So we're going to watch him do them and then we're going to do examples ourselves. But before we get to that, in 7.1, we're going to be looking at a 2-dimensional feature that we're going to need in sections 2 and 3. Okay? So this is area of a region between 2 curves. And we're going to consider this image. So I don't think, is this drawn in your notes now? Wonderful. Okay, I got it in there. So we're going to consider the graph of f and g below. And if we wanted to find that green shaded area between the curves, right, between A and B, then what we would want to do is we would want to take the antiderivative of f of x, which gives us the area all the way down to the x-axis, right? And we would want to subtract off the area of g of x, which gives us the part that's not shaded in right now. It's this piece, yeah? And that would give me the trapped green area. Does that make sense? Okay, so this is an area subtraction problem. That there's actually a fact about this that you have seen before back in chapter 4 in Calc 1. If you have the area, or the antiderivative of f of x minus the antiderivative of g of x, you could just subtract f of x and g of x first, and then find the antiderivative. Okay? You can also do it the other way, right? We could find the 2 separate antiderivatives and so forth, but sometimes it's easier to combine those and subtract those first, and then find the antiderivative second. And this is all from A to B, specifically for our drawing. Put those in. So we are going to have to be able to graph a little bit in 2 dimensions. You're welcome to have your calculator to assist with doing that. Some graphs are more familiar to us than others, especially in terms of their specific details. So if you'd like to, go ahead and grab your calculator out. And example number 1 does not ask us to find any area. So don't go overdoing what the questions ask you to do. All this asks us to do is to sketch the graph that this is referring to. Okay? Sketching the graph. So this piece right here is going to be our f of x graph. And this piece right here is going to be our g of x graph. And I know, at the very least, that you know how to draw g of x. What does g of x look like? Let me put it over here. What is it? Yeah. It's just a parabola. Joshua's putting his hand in the hair, sort of showing the imagery of it. Oops, I need to have a right tool, excuse me. It looks, whoa, that's not it at all. Let's try again. That's not too bad. So this is the g of x function. So g of x, and we'll call it, or say that it equals x squared. The other graph is also a graph of a parabola, right? But how does this parabola look different than the first one? Okay, it's shifted up, the 2, and then what else? It is flipped upside down because there's a negative in front of it. Exactly. So if we took this whole graph, shifted it up 2, and then we reflected it down, we'd have an image that looks something like this. And this would be our f of x equals 2 minus x squared. Okay? It says that we're supposed to graph this between -1 and 1. Now, in your calculator, in case you just had a graph, especially that wasn't quite so friendly, if we put in 2 minus x squared as one of our y values, and the other y value is the x squared, and we graph it, just a zoom 6 window is fine. It'll look like this picture, but it'll be kind of zoomed out more, right? We'll have two parabolas, one opening up, one opening down. If you want to find these corners to see where they're crossing one another, you can do that in a variety of ways. One way you can do that is by using the intersect feature. So do you see along the top of your screen, there's like little blue letters? Okay, mine are blue. Yours may be yellow or something like that. But they say it above the buttons. Do you see the buttons? They say it above it. There's one that says calc. Do you see that? C-A-L-C? Okay. That's the one we want. So the way you get that button, right, where it's the one that's above, is you hit the second key, and then you hit the button that's got the word calc above it, which is the button that says trace. So So you should have a menu now that says calculate. Does everybody have a menu that says calculate? And I don't know how yours does it here on your calculator, so you might have to play around with it a little bit, okay? So number 5 on this one should say intersect. Does it say that? Excellent. Choose number 5. It's going to ask you some questions. It's going to say first curve, second curve, and guess. The first time you do this, just press enter 3 times. First curve, enter. Second curve, enter. Guess, enter. And it's going to give you one of the 2 of the intersections. It gives me on mine 1, 1. So it tells me over here that this point right here, I haven't drawn it very well, but I'll just write it in as 1, 1. Okay, my scale's off in my picture. That's fine. It's 1, 1. Now, from symmetry, you probably know that the other one's going to be negative 1, 1. And not everything's going to have symmetry, so I want to show you how you find it if that's not the case. So go into the calc menu the same way. Second, trace. Choose number 5 where it says intersect. When it says first curve, press enter. When it says second curve, press enter, but don't press enter for the guess. You need to move your cursor closer to the other point that you do not know the intersection of. So just move your cursor to the left-hand side, and when you're close-ish to the other intersection spot, press enter, and then it will tell you that spot as well. So this piece over here is negative 1, 1. Now that's very friendly. It's very friendly because these x values that are showing up are the same x values that it wants me to go between, right? It wants me to go between negative 1 and 1. Agreed? So that's very friendly. If it weren't that friendly, it'd be okay. It would end up with a graph like this where we drop these red lines. They don't have to be intersection spots to do that. This one just happens that they are. So if I wanted to actually shade the region, which it says I'm supposed to here, I'm trying to shade this region right here in between because the intersection spots, negative 1 and 1, are in fact the limits of integration that I was told to use. Okay. Is the visual okay? Does it make sense? Okay, let's try another one then, where we're actually going to calculate something. All right, now this one's a little different. Can you see why this one's a little different? Ooh, it's in terms of y. Do you see that? It says f of y equals y squared, g of y equals y squared. And it really means y. It's not just like when they change, the x's to s's and the y's to t's or something like that, right? It's not like that. It really means y. So as a reference point, real quick, I'd like to write this down in terms of x equals. This is the equation x equals y squared and x equals y plus 2. Let's ignore the first one for a moment. The second one's easier to deal with. We can take this one pretty easily and resolve it for y. Yeah? What is this in terms of y equals? Yep, y equals x minus 2. So I can subtract my 2 to the other side. I shifted mine around in the same process because I like my y's on the left. Leave your y on the right if you want, doesn't matter. But we know how to graph y equals x minus 2. It's a line with a slope of what? No. Slope of 1, and then the y-intercept is negative 2. Yeah. Okay, so we've got a y-intercept of negative 2. We've got a slope of 1, so it goes from here up 1 over 1 a couple of times. So it looks like that, and I'll draw in a line that goes with that. We'll make it red. Something like that. So this is the red one. Okay. Now, you know what the graph of y equals x squared looks like, but this says x equals y squared. Do you know what that looks like? It's not a function.
Y equals the square root of x.
Okay, so that's a good first thought. If I were to try to solve this for y, it would say y equals the square root of x. But that's a little bit incomplete. I need a plus or minus. So when I put a square root into a problem, there is a plus or a minus. If you don't like taking the square root, I'm going to show you another option how to think about this, but this works well too. If I were to graph in the calculator this equation, okay, if I actually put this in, I have to put this into 2 different locations for y. One of them that says y equals square root of x, and one of them that says that y equals negative square root of x. That's how you have to put it into your calculator. Your calculator requires function notation, okay? So if you wanted to graph this one, you will see that that's what it'll do. If you put in the square root of x, it's going to look like this. If you put in the negative square root of x, it's going to look like this. Now, what image did we get? A parabola, except that what? It's on its side. Now, does that make sense? If this is my y-axis, I'm sorry, I said that wrong. If this is my x-axis, which it is, and this one's my y-axis, and normally, if it were y equal x squared, it would be opening up around the y-axis. Then if it's x equals y squared, it's going to be opening sideways along the x-axis. So you don't have to solve this other one the way that we did. If you can visualize, I know this is a parabola. It's just not a parabola opening upwards. It's a parabola opening sidewards. Caleb.
I'm just thinking like
Okay.
twist.
Mm-hmm.
Trying to visualize it
Yeah.
differently.
Now you have to draw these graphs out far enough to see what's happening, right? Because this one actually doesn't give you limits of integration. This one did. It told you to go from -1 to 1. Agreed? Yeah. This one doesn't. It tells you find the bounded area, which means you actually have to figure out what those bounds are. So one of mine, very nicely, is kind of already graphed, and it's not wrong. This point right here is one of the intercepts. The other one is up here, and I don't actually have it yet. But you could get it again with your calculator, right? So if you wanted to do this in the calculator, you could put in the graph of y equals x minus 2, right? We have that one, that's my red line. And you could put in the square root of x, and you would look for the intersect. So you can totally do that. You can do the same thing for the lower half. You can put in y equals x plus minus 2, and you can put in y equals negative square root of x, and you will find that intersection in the same way. So if you would like to use your calculator, you may. There is another way to find that, and I'd like to show you what that is from an algebraic standpoint, because sometimes it's not real friendly, or the calculator gives you irrational numbers, and we want to have them exact, so we wouldn't be able to use the calculator to get those values. So what do we do when that happens? Well, what we want is we want f of y to equal g of y. That's our goal. Well, f of y is y squared, and g of y is y plus 2. Now, with the exception of the fact that these have y's in them, do we know how to solve an equation like this? You do. You may not have done it in a minute, but you do. This is an algebra topic. Okay, you would have seen this in an Algebra 2 course, college algebra course, pre-calc course, potentially even depending on what happened, you might have seen it in a Trig or Calc 1 course. Okay, how do we do this? Well, I'll tell you what you don't do. You don't take the square root right here because there's a y on both sides. Okay, we've got to get everything. If y is squared, which it is, we need to get everything on the same side for starters. So the first thing I'm going to do is I'm going to move my y and my 2 over with the y squared. Now, in this form, it probably looks like something that you think, I know what it's supposed to do now. So, David, what do we need to do now? We need to factor, and we hope it factors. And what do we do if it doesn't factor? Quadratic formula or completing the square. Right? Those are your choices. Now, as I would have done it, this does factor. It's not bad. Okay, it will factor. So let's give this a go. All right, so I've got y and y. What are the signs going to have to be in order for this to work? Yep, one positive and one negative. How'd you know, Andrew?
Because the negative.
Yep. The negative 2 at the end tells us that we need one of each. Okay. I also now need the last two numbers to multiply to give me 2, which means I don't really have choice, right? There's only two numbers that multiply to 2. 1 and 2, right? So I'm going to put them in, and if I put them in backwards, we'll be able to see that pretty quickly. So if we want to check and see if we put them in the right place, we check the inner and the outer terms. The inner term here is positive y. The outer term is negative 2y. If I add them together, what do I get? Negative y. Is that what I wanted? Yeah. So we put them in the right place. And if we had not gotten negative y, we would say, okay, got to switch them. We switch them, and then they would be correct if it factors at all. This one does. So what this tells me now, make this a little bit smaller, is that I have two values for y. I have y plus 1 equals 0, so that's y equals negative 1, and y minus 2 equals 0, so y is 2. right? So I set each piece equal to 0, and I get y is -1 and y is 2. That's not an ordered pair. That's two values for y, right? If I'm thinking about listing these, I have found -1 here, and I have found a 2 here. Is everybody with me on that? Okay. How can I find the corresponding x value that goes with that? I got lots of equations everywhere all over the paper, right? So pick your favorite. You can use one of the ones that was originally given to us. You can use one of those that we have changed into y equals form. I actually think the x equal form ones are probably easier to use because we're trying to figure out what x is. So if I put in the number -1 for y into either of those equations, what will x equal? 1. If I put the number 2 in for y, what will x equal? 4. So this other point at the top, whether I used the calculator or whether I did a little bit of algebra here, is the 0.42. Now, we can shade in the region, and we can see what this is doing now from the perspective of the shading. And I need to find this area. Now, notice what I have a problem with doing here. On these graphs, two things. Number one, they were solved for y equals, and ours is solved for x equals. Number two, when I solved this to say x equals, I didn't get 2 equations, I got 3 because of the plus or minus, right? So normally what I'm doing is I'm subtracting the taller curve, right, the higher one up minus the lower one. But the problem is that the higher one up minus the lower one gives me an issue over here. Over here, that blue piece is not trapped between the first equation and the second equation that I was given, is it? It's actually trapped between itself, right? The top is x squared and the bottom is -x squared. And so it's very messy for us to actually do the subtraction in the order that we're used to. So what do we do instead? Well, instead we do it in terms of y. So normally it's top minus bottom, right? Because the positive y values are on the top, negatives on the bottom. So instead we're going to do it where we're going to do the rightmost, that's not a waves, the rightmost equation minus the leftmost equation. So in some sense now, let's try the orange. We're going to be subtracting this direction, right? We're going to subtract this first equation here. Let me do it that way, actually. We're going to subtract this top equation. It's now the top equation, right? It's the biggest x values minus the bottom equation, which is the biggest, smallest x values. So what does that look like? Well, do I have another slide? I do. Okay. Let me actually take my image and put it on this other slide. Okay, so the line, the red one, right, is my rightmost equation. And in terms of y, I'll write these at the top. The first equation is f of y equals y squared. The second equation, the one that I drew in red, is f of y equals y plus 2. So this is my top equation, right? My rightmost equation, it's y plus 2. And I need to subtract the left equation, which is y squared. Okay? Right equation minus left equation, because it was given in terms of y, it works better that way. There's one more thing that's tricky. These limits of integration here, -1 and 1, what variable do they apply to on this graph? They apply to the x variable, right? And we know that, and that's that dx on the end. So those of you who took Calc 1 with me, I know for sure that at some point we talked about the fact that that dx on the end is not just the end of the problem and sort of like the ending parenthesis. It has more meaning, but we weren't ready to talk about what, right? That dx on the end here is telling you the variable I'm working with is x. Notice what I did when I wrote this out. I didn't write dx. I wrote dy because the variable I'm working with is y, right? What that means is that these limits of integration that I need to write in on the top and the bottom need to be in terms of what variable? y. I don't need the x component here. I need the y component. So what are my y components when I'm looking at the limits where they intersect? Yeah, the -1 and the 2, right? So over here, we're going to have -1 and we're going to have 2. Okay? I know I just turned your world on its side, quite literally. Everything changed is now in terms of y. But the processing of this will work exactly the same. What's the antiderivative of y? Well, it's y squared over 2. What's the antiderivative of 2? 2y, because we're doing y's, yep. And what would the antiderivative of y squared be? Y cubed over 3.
So we don't do dy dx?
Okay, so dy dx is what we do when we're doing derivatives. This is antiderivatives.
Oh.
Yes. That's okay. No, you're processing. That's good. Yeah, we're doing antiderivatives. Am I done? Oh, no. I'm not going to have a plus C on this one because I have limits of integration. Yeah. So I'm going to go from 2 on the top down to -1 on the bottom. And I'm going to evaluate this at each of those values. So I have 2 squared over 2 plus 2 times 2 minus 2 cubed over 3. All of that is minus -1 squared over 2 plus 2 times -1 plus -1 cubed over 3. That's fine. Some of these pieces clean up faster than others. You're welcome to use your calculator to clean this up as well. It's all fractions. Your calculator can add and subtract fractions. It's no big deal. It's going to give you back fractions. We're not going to deal with any irrational numbers. All that's just fine. I'll do it by hand on the screen, but feel free to grab your calculator to verify. 2 squared is 4 over 2 gives me 2 here. 2 times 2 is 4. And then I have 2 cubed, which is 8 over 3, minus. -1 squared is 1 over 2. 2 times -1 would be -2 in the middle. And then I have -1 over 3 at the end, which gives me cubed, -1 cubed over 3, which gives me -1 over 3. Or if you prefer, you can consolidate this and write this just as -1/3 at the end. Okay? Yeah. Did I miss something?
E positive. So last term was subtracted.
The last term subtracted, you mean like this piece?
Like it's minus y cubed over 3.
Mm-hmm.
But then in the second, it's plus -1 cubed over 3 instead of minus -1 cubed over 3.
Do you mean right here? Did I miss that one?
Yeah, but like above it, should that be positive or negative?
It should be negative. Thank you. We'll get those fixed. Perfect. Appreciate it, Andrew. Okay, cool. Consolidating some pieces. This is going to be 2 plus 4 is 6 minus 8/3. Minus, let's see, I have 1/2 and -2. That's -3/2. And then I have plus my 1/3 here. I have 8/3 here, -8/3, and then the -1/3 makes -9/3, which would be 6 minus 3, and then plus 3/2. So I think I've got 3 plus 3/2. And if I get a common denominator, that's going to give me 9/2. That's what I have written down. So I hope that I've got all the pieces there correct. 9/2. And again, you don't have to calculate that out. Just grab your calculator, stick it in there. It's going to spit back out a fraction for you. If you don't know how to turn your values in your calculator back into fractions and they just are in decimal form, let me know. I can show you. It's not hard. Okay, you ready to try another one? This one's the most interesting graph of the day, for sure. Okay, so the last one, the one we just did, that's interesting because we flipped it on its side. The next one's more interesting in terms of the image that shows up. And that happens because we're dealing with some trig. Okay? So this one says, again, sketch the region, find the bounded area. So the directions are much the same as we had on the last problem. They do give us the limits of integration. They're going from negative pi thirds to pi thirds, so that's friendly. They're also in terms of x, so we're not turning our head on its side to think about this when this will be in our standard form. All right, so the graph of 2 sine x. You know what the graph of sine x looks like, right? Sinusoidal curves, they've got these curves going on. What's that 2 do at the beginning? As it shift it, it stretches it up, right? So it makes it have an amplitude of 2. So if I'm taking a sketch of this one, the graph of the sine of x from negative pi thirds to pi thirds only is going to look incomplete in terms of sine, but it actually looks something like this. It doesn't give us the full peak and valley, so they're not quite as arced maybe as I've drawn, but it has this sort of general shape to it. Again, you're welcome to use your calculator. If you put this in, you can put in 2 sine of x, and then, oops, hit the right buttons. And then in y, you can put in tangent of x, y2, you can put in tangent of x. You want your window to go from negative pi over 3 to pi over 3. Your y min and y max, if you want to manipulate with those, do not need to go from negative 10 to 10, right? This sine curve can't go any higher than 2, and it's not even going to quite get there. So if you'd like to go from negative 2 to 2 to give you a more zoomed in kind of graph, that would be quite reasonable. So the first graph looks much like what I described. The second graph actually looks kind of like, whoops, this. We've got like a bow tie, right? It's not quite a bow tie, but we've got, how about, I don't know, this looks like something I should throw. Some sort of a boomerang kind of thing. What did you describe it? A propeller. Yes, it looks like a propeller, like the little leaf things that fall off the tree. Propellers even, right? You've seen those? Okay. So the bounded region is in here. And we know where it starts and stops because they gave it to us. It's negative pi over 3 and pi over 3. Now, at the original one, this graph up here was the sine of x. Sorry, I should have put y equals. Let's put that in. I'm going to change the color of the other one to try to distinguish it for us. The other graph, oh, and it wasn't that top one. I apologize. Let's undo that. Yes, it's actually this, oh no, it was that top one. Let's get that in there. 2 sine of x. Thank you. Okay, the little bit of a, oh, that's not going to work. Okay, this bottom one right here that flips up over here is the tangent one. So this is y equals tangent of x. Okay, pretty good. Now, how is this one different than the others that we've done? Because it is uniquely different in a way. They're 2 separate areas. Why does it need to be 2 separate areas, Andrew?
Because they're like, separate.
Okay, so let me add a little bit of vocabulary to what you said. They cross themselves, right? The curves actually cross in the middle. Not only that, but do you notice that they flip-flop their locations? On the right-hand side, which graph's on top? The sine graph. But on the left-hand side, which graph's on top? The tangent graph. You with me? So we do get 2 integrations on this. Now, there's another way to do it. I'm going to do it the way we've just described, and then I'm going to show you a variation. But we do get 2 integrations. So I'm going to have the integral. Both of them are going to have reflections or variations of the limits of integration. The first interval, I'm going to actually do it from left to right. The leftmost place where they intersect is what? Negative pi over 3. And where do they intersect the second time? At 0, right? So it's going to go from negative pi over 3 to 0. And which graph is on top? The tangent graph's on top on the left. So this is tangent x minus sine x. Thank you. I keep forgetting my 2. David's going to keep me on track. Thank you. All right, cool. And I put the dx on the end, indicates the variable I'm working with, right? Dx. And to that, I'm going to add the integral. Where does this integral on the right start? Okay, it starts at 0 and then ends at pi over 3. Which graph is on top? 2 sine of x is on top. And what's on bottom? Tangent of x. Dx on the end. Okay. I mean, like, yeah, the subtractions are in a different order, but the integrals I'm going to take are the same integrals, right? Right? I mean, the integral of tangent, integral of 2 sine, they're going to be the same. Yes, sir?
Not just output the same value.
What'd you say?
Could we not just take one of those integrals and then multiply it by 2 because they're the same?
Yeah, that's another option. We'll get there. You're right, we could. There's a third option as well that we'll see. This one has a lot of symmetry, right? So what David's noticing is that whatever these little blue area, like leaf shapes are, it's just doubled. So we could just find one of them and double it. And that's one of the methods I'm going to show you in a minute. So very good observation. There's a second not issue, but there's a second way to think about this too that we'll look at beyond that. So let's go with what we've got so far first, and we'll see that doubling feature is in fact going on. So what is the antiderivative of tangent of x? Yeah, that's one of those ln ones. Ln of the absolute value of cosine of x. And does it have a negative on it? Yep, a negative on it. And then we won't have any plus c's because we're going to do limits of integration with our numbers. So we don't have to do the plus c parts of it. And then minus, what's the antiderivative of sine? It is negative cosine, so I'm going to get a positive here now, right? So positive 2 cosine of x. And this one's limits of integration go from 0 to negative pi over 3. I think I would probably, I think I'd prefer to be on the next screen and have more space. So I'm going to copy this and do that. All right, the other one over here. Now I've got the integral of 2 sine. That's going to be, let's do it like this. That's going to be negative 2 cosine of x. And then the negative tangent is going to end up being a positive natural log of the absolute value of cosine of x. Bracket on the end, and then limits of integration here are pi over 3 down to 0. Okay, we're going to be putting in negative pi over 3 first. So negative natural log of the cosine of negative pi over 3 plus 2 cosine of negative pi over 3. And then minus, plugging in zeros everywhere. So minus negative natural log of the cosine of 0 plus 2 cosine of 0. Like so. All right. Lots of signs going on to keep track of. Let's hope that we can do that. What happens when I do the cosine of negative angles? Do you remember? Like cosine of negative pi over 3 compared to cosine of pi over 3. We're going backwards around the unit circle. That's true. But do you know what kind of answers that I get for cosine when I take that angle measure? Whether it's positive or negative? Okay, so if you haven't done so, you're welcome to look up and write this down. You probably haven't seen it in a while. It's something called even and odd identities. The graph of cosine is what we consider or call an even graph, and it's because it's got symmetry around the x-axis. And the even property that I'm referring to is that the cosine of negative x is the same as the cosine of x. The negatives don't affect the value of cosine. And if you don't like x, put theta in there, whatever. The cosine of negative theta is equal to the cosine of theta. So these negatives here don't matter in terms of finding my cosine value because cosine is an even function. Sine is an odd function. If we were doing this for sine, the sine of negative x is actually the opposite of the sine of x. Okay, these are even odd identities. They come from trig discussions that you probably haven't thought about in a while. Point being that we can actually look at this and see what the cosine of negative pi over 3 is by just knowing the cosine of pi over 3. All right, unit circle. What is the cosine of pi over 3? It is 1/2. So this is negative natural log of 1/2 plus 2 times 1/2 minus. Now what's the natural, or what is the cosine of 0? This is minus and negative, so I'll do plus. Yeah, the cosine of 0 is actually the number 1. So this negative distributing through here gives me a negative over here, and I have 2 times 1 over here. Okay, that's half of it. We have this other half over here to do, right? But it's going to have all the same pieces, right? All the same things are going to sort of come out of this. So we're going to have plus, and then I'm going to have negative 2 cosine of pi over 3 plus the natural log of the cosine of pi over 3. And then all of that is going to be minus negative 2 cosine of 0. That's 0, not theta, 0. Plus the natural log of the absolute value of cosine of 0. Okay. So this part at the beginning. If I get that copied and pasted. It's right here again. And over here I have minus 2. We said the cosine of pi over 3 is 1/2. And then plus the natural log. Again, cosine of pi over 3 is 1/2. So you don't really need absolute values, so 1/2. Minus a negative, so this one will cancel and distribute through. So have plus 2 cosine of 0, which was 1/2. I'm sorry, is 1. Get my numbers straight, 1. And then I'm a tiny bit out of space. So let me shrink it just a little bit. Plus the natural log of 1, because cosine of 0 is 1. Okay, do I have all the pieces in there? Gracious me. Oh, this was a negative. It's not going to matter, but that's okay. That's a negative. All right, let's start with that. What's the natural log of 1? 0. Wonderful news. Let's at least cancel that out. It would have canceled out either way because there's a positive one here and a negative one here, but they're 0 anyway. We've got some 1s coming out of this too, correct? So let's see, I've got negative natural log of 1/2 plus 2 times 1/2, which is 1. What is going on there? There we go. Did I get it right now? Okay. Minus a 2 here. And then I have minus a 1 here. I've got plus the natural log of 1/2. And then I have plus 2. Okay. Negative 2 and positive 2. Negative 1 and positive 1. And then something happened because I shouldn't be ending up with zeros everywhere. What did I mess up on? Where did my signs get off? This is what happens when you go off script and aren't following your own notes. I think my signs, I don't know. All right, let's come in here and do this. We're going to go back to what David did. We're going to double it. I've lost a sign. My negative sign disappeared, and so everything's canceling out to 0, and it shouldn't be. Sorry. That's all right. We'll get it fixed. All right, so if I fix it, let's try it again. This one's a 1. This one's a 0. So now I have negative the natural log of 1/2. And then I have, and then I have, what was it? Sorry. Negative 1. And all of this is doubled, so times 2. That's where I'm off. The first half signs is off, so this should actually be doubled. So this should be 2 natural log of 1/2 plus 2. Something's wrong with my signs. I don't know what I'm doing. Those are supposed to be positives. I screwed something up on my signs somewhere. What did I screw up? Any ideas? Would somebody look up real quick and tell me, is the tangent absolutely negative natural log of cosine, or is it positive?
Yeah, I just think it's solid.
You looked it up and it's
negative value.
okay.
I got that.
All right. I'm not sure what I've got going on. Yeah, I've got it written in my notes that way too. But I've got to sign off somewhere. This is what it's supposed to be. This is what it's supposed to be. It's what it's supposed to be. I do want to make mention, so doubling things was one of the things I was going to make mention of that David said, which is great to notice that each of those two regions are symmetric, so we're going to have double that amount. That's wonderful. The other thing that I want you to notice, which is going to be a little bit more helpful into the future, is these integrals, what's inside of them, the integrand inside, are identical except they're backwards, correct? Everybody got that? They're backwards. So what we could do, instead of actually finding these and looking at, which one is on top of which one, right? On one side, it was the top when the bottom switched to the other side, correct? Is that we could actually set this up so that we're looking at the integral from negative pi over 3 to 0, for example, and we just take the absolute value of the 2 sine of x. How did I write it? I think that's backwards what I wrote. Tangent of x. Tangent of x. Plus, minus 2 sine of x. And then my signs would for sure be right because I'm taking absolute values. So no matter what I get inside of the absolute values, it's going to actually end up being a positive when I'm done with it, right? And then I can do the same thing for the other half. So this would work even if it weren't symmetric. I could then go from 0 to pi thirds. I can take the absolute value. I can still do tangent of x minus 2 sine of x, like so. And it doesn't matter whether I write the tangent first or the sine first, because when I take the absolute value, it's going to fix the signs anyway. So even if these two weren't identical and I wasn't able to double them, which I was, right? Even if I do the absolute value of each of the pieces, I can ignore the fact that the signs are different, and I can do it from that perspective. I want to show you one more cool thing. So David, Joshua, and Andrew have already seen this before, but in case you haven't seen this before, I think it's good for you to see it, okay? So I want you to take your calculator. We're going to actually use the graphs that we have. So I'd like for you to put in y equals the subtraction. We'll just go with the order that it's given here. This one right here. I would like for you to write in tangent of x minus 2 sine of x. Now it's not going to look like the graph that we just drew because I've merged it all into one equation. Okay, but just put in tangent of x minus 2 sine of x, and I'm just going to let just have your window go from 0 to pi over 3, and I'll sketch what I've got on the board or on the screen up here. So it's a very strange looking kind of graph right now because I've done the subtraction and it's below the x-axis. It's down here like that. Does yours look like that? Okay, wonderful. So one of the things that we keep doing is integration, and it's finding this trapped area. Now the trapped area in this case is going to be this area between the x-axis. It's going to be this piece here. Okay? Your calculator can find that. Now, it won't put it in irrational form, but it would at least confirm for you if your irrational form was correct because it would give you a decimal approximation. So we're going to give this a go. The way that you do this, there's two ways to do it. The way that's most maybe satisfying is the graphing way itself. So what we're going to do is, do you remember that calc menu we went to before? It was second trace. Click on that. Click second trace. Do you see option number 7? Does anybody see it? Does it look like a script S, like what we're doing? That's the one we're going to use. So choose number 7. It says lower limit. Our lower limit here is the 0. So you press 0, you press enter. It says upper limit, and you're going to type in pi over 3, because that's our upper limit here. And you're going to press enter. Oh, man. Why doesn't it like... Make your window go a little bit bigger, maybe. Make it go from negative 0.1 to 1.1. Let's try it again.
You said what?
All right, I'm just doing negative 0.1 to 1.1. go back in and do it again. I think it's because the window's just not quite big enough. It's doing it. Your calculator approximates things all the time. It doesn't really know how to do calculus. So let's try it again. Lower limit 0, upper limit pi over 3. Now it works. Get shaded in. I don't think you've got your subtraction set up right because you don't have this picture to begin with.
It's right there.
Oh, yours is zoomed out. That's
Zoomed
fine.
out
Okay.
very
Yours
large.
Zoomed out very, very large. Did it shade it in like this? Do you see the number at the bottom? My number says negative 0.3068528. Does yours say something like that? Very close? Negative 0.3-ish? Does it say that? Okay. So let's check real quick. So this says negative 0.3068-ish. So go back to what we said our equation's value was here. And I want you to type into the regular screen 2 natural log of 0.5 plus 2. And I want you to divide it by 2 because we only did half of the interval. We went from 0 to pi thirds. If you divide it by 2, you should find that it's the same value. Did it work? I mean, it's a positive versus a negative because ours is the negative with the graph underneath the x-axis. Okay? If it were a whole number value, that'd be friendlier because then you could actually prove in your mind that it worked exactly. But you can at least get that the decimals match up when you look at the decimal approximation that we got from the other version. If I hadn't lost a sign somewhere along the way, I'll figure it out, but that's okay. All right, any questions? All right.